I am ready whenever you are.
All right. Well, hi, everybody. Welcome to our chart speaker series. And this is my pleasure today to introduce Professor Missy Cummings, who's been a good friend for a long time and a valued colleague. She received her BS in math from the U.S. Naval Academy in 1988. And her MS in Space Systems Engineering from the Naval Postgraduate School in 1994, and her PhD in Systems Engineering from UVA in 2004. And she was one of the US Navy's first female fighter pilots, and she has some really cool stories that she could share on that. She's currently professor in the Duke University Electrical and Computer Engineering Department and director of the Humans and Autonomy Laboratory. She's an AIA fellow, a member of the Defense Innovation Board, and a member of the Veneer Incorporated Board of Directors. So it's my pleasure to introduce Dr. Missy Cummings.
Why, thank you, Nancy. And I just want to, I forgot to update my bio. I was formerly on the Defense Innovation Board. Every single one of us was fired with the change. A couple of weeks ago, Secretary Austin said, "You're all fired." He had to do some house cleaning. So stay tuned. They're going to reform some boards, and this may apply to, who knows what's going to happen to the Defense Science Board, because they were all fired too. So stay tuned. It's always interesting with the DC world. All right, I'm going to take control of the screen, if that's okay. And I thank you for inviting me. We are longtime friends. I would have rather, especially it being winter, I would have rather come out and done this in person, and had a lot of fun out there. We go way back, but we still have a lot of connections. I see Hudson Graham, he's on the line. He's one of my former master's students, now getting a PhD. So I was so glad that that was able to come to fruition. Li Xiao Wang, she is a former postdoc with me, also now working for Nancy. So there's almost kind of like this highway, which I'm happy for. Unfortunately, I'm not putting out nearly as many people as I should. I think that's true for everybody that works in autonomy right now. Okay, so I'm going to tell you, it's kind of like a meander through the things that we're working on my lab, but they really all have this common theme of how do we model for human autonomy interaction? Then how would those models inform design? And then how would you test these systems to know that they're working correctly? And so this is really kind of a systems engineering approach to human autonomy teaming, which I really call human systems engineering. You'll see cognitive systems engineering, cognitive like there's so many different names. I wish we could all agree on one set of names, because I think it would make us a stronger field, but it's really looking at, and in your labs, you guys call it human autonomy teaming. It's all kind of the same bucket, but really that systems engineering approach of requirements, modeling, design, testing, and then the feedback loop. I think that's the really important part. So if I were to tell you what is the overarching principle that guides the work that I do in my lab, it really comes down to this framework, which I built on top of a framework that Jens Rasmussen built. He originally came up with the skills, rule, knowledge-based reasoning framework. And this is where, any entity in the world, whether or not we're talking about humans or intelligent agents, AI, automation, whatever you want to call it, each of these entities has to step through these stages to be able to do reasoning in the world that we know. So for example, in the driving scenario here, skill-based reasoning for you is learning to take the signs and signals that you see in the world and automate them to a degree that your response is very automatic, right? So when you first learn to drive, you have to tell yourself to keep in between the white lines. But you do that for 20 minutes and you've got it. Your brain has that wired. So that is a skill that you were able to learn quickly. It became highly automatic. And indeed, it stays for humans, it stays highly automatic until your sensors degrade. And that would be when you start to have vision problem. And indeed, you'll see old people pinging between the lanes, and that's because their sensors and that feedback loop in their head is starting to degrade. Once you've got skills figured out for whatever task it is you're doing, then you go to rule-based reasoning. And rule-based is you see signs and symbols in the world, you understand that there's a set of actions, procedures that need to go along with that. You see a stop sign, you know that you have to start slowing down, bring the wheels to a full stop, look all the ways, and then make a turn. You know, there's the conditions in the world dictate what rules and procedures you should follow. And then once you have figure that out, then now you have spare cognitive resources to elevate to knowledge-based reasoning. And we would think about this in human factors terms, we would call that judgment under uncertainty. There's a situation in front of you, you have some knowledge about the world, you have to maybe do some fast simulations in your head, you've got some signs and signals, but it's not absolutely clear. So there's some uncertainty there. And indeed, this arrow of uncertainty is one of the things that I added to this framework, as well as the addition of expert-based reasoning. Because this uncertainty, you need skills, uncertainty is generally low to adapt for skill-based reasoning, but you need to adapt rule and knowledge-based reasoning, and then ultimately what I call expert-based reasoning to master all situations. Now, in this example, I show you that there's a partially occluded stop sign. So, you know, your brains, everyone who has normal vision or even nearly normal vision can tell that that partially occluded stop sign is a stop sign. I don't have to fill in the gaps for you. Your brain automatically understands, even though the symbol in the world is a little uncertain, you're able to fill in that uncertainty gap and you know it is a stop sign. And this is actually where we start to see automation, autonomy start to break down. Really, once we get past that rule base, now we start to see that if autonomy cannot understand the world, the uncertainty in the world, then it starts to fail. Indeed, one of the things that we know from self-driving cars are partially obscured stop signs are a big problem for most computer vision systems, if not all. Because if these partially obscured stop signs were not in the underlying training set of data, then the system doesn't know, but it has to be almost exactly in this way, trained exactly in this way. A self-driving car, if it sees a stop sign with a ½ inch of snow on it, it doesn't know if it's a stop sign. If it sees a 3/4 inch, it doesn't know that that is the same as a ½ inch and that that is a stop sign, right? So you could extrapolate that. There's a lot of conditions, and indeed, this is what makes autonomy, underlying autonomy, so brittle. And that's where then we make the leap to expert-based reasoning. So expert-based reasoning happens when you've got maximum uncertainty. There is no way, shape, or form that you've ever had any information to potentially give you insight into how you must solve this problem. I like to use Miracle on the Hudson for Chesley Sullenberger. He had to reason through that. He has experience. He has some signs and symbols in the world. He has procedures. They're not exactly, they don't cover all the bases. And it wasn't clear if, if his procedures, if he executed them correctly, was that situation going to end up as well as it did? And so experts are those people in the world that have to reason under maximum uncertainty. They have to pull almost completely from top-down reasoning to figure out what to happen. And I love this sign. This is this is actually an intersection, or it was somewhere in the world, where somehow if you got to this stop sign, in theory, you could not move. You couldn't go left, right, forward, or turn around. And, obviously there was somehow a mistake that you got there, yet people can get there. And if a self-driving car saw this, the self-driving car would not move because it would read each one of these signs and would not go anywhere. But indeed, a human understands, look, I got to move. And most likely it means that if I got there and I'm facing this way, it means I'm going to have to do a U-turn, which means I'm going to have to break one of these rules. But we understand that, within the fabric of the society that we're in, sometimes there has to be some kind of give and take to operate safely in the world. And indeed, we've seen this with shuttles that don't understand not to back up, or that a tractor trailer was backing into it and that it needed to back up, even though that was an unwritten agreement it is still yet an agreement that exists in the world. So autonomous systems do really well at bottom-up reasoning, and humans, their strength is really top-down reasoning, particularly under maximum uncertainty. And so this whole relationship is what drives everything that we do in my lab, because we're trying to figure out, and you can see this as a teaming, right? There's autonomy at the bottom of this SRKE framework. There's top-down reasoning, humans at the top. We've got to figure out how to have these, when to have them meet in the middle, and how we should have them meet in the middle. Okay, so this is probably the most fun project that we've done recently, and we've been working with the U.S. Department of Transportation to think about how should we develop protocols for certification of L2, L3 vehicles, driver monitoring systems. And this really is looking at the L2, L3 is when a human is expected to take over in some way, shape, or form, right? So now we've got autonomy doing some of the bottom end of the curve, humans babysitting at the top of the curve, and somehow we need to have them effectively meet in the middle. So the first question we needed to ask was, all right, well, for these driver monitoring systems, while there have been some test drives from companies and Consumer Reports, there was really no data out there to indicate just how variable the alerting and the driver monitoring systems were. So we had no idea, are these systems, and in these systems I'm specifically talking about are Tesla Model 3s. Are they reliable in their alerting? Is the computer vision system reliable? I mean, how much uncertainty are we actually dealing with? So we set up a camera system that allows us to see outside the car, sees the driver, sees the display. And the good thing about the system is you can pick it up and put it into any car, right? So it's not hard mounted. So it's easily modularized so that you can move it quickly from car to car. So I'm not going to spend a lot of time going, this is the presentation about this set of tests takes an hour and a half. So maybe some other time, if you're really interested about that, I'll tell you more. But this is an example of a test that we did where the Tesla is going down a road with lines and the edge of the road, and supposedly the Tesla has emergency departure system. So if the driver is not paying attention and the car is headed off the road, the car is supposed to detect that and then pull the driver back on. Indeed, Elon Musk has advertised this as an amazing capability. So we did a bunch of tests. We have access to a closed track here in North Carolina. It's good to be a NASCAR country sometimes. And so we had statistical significance. We drove these cars over and over and over again. And this is just one of many runs. So yeah, whoa, the student, my poor student who has post-traumatic stress disorder after these tests, if he had not taken control there, he would have barreled off and, potentially died. I mean, we're on a safe track, so it was not a big deal, but you could imagine there have been many cases where Teslas have unexpectedly run off the road, and this is, it's easy to see how this could happen. So in this particular test, this is what we call the lane departure test. There were 30 trials, 10 cars, 10 trials for each car. We had 3 different cars that we just rented, by the way, just randomly rented 3 Tesla Model 3s, 2018 Model 3s. And one of the things that you should see is, first of all, 47% of the trial did not generate any alert. So that's the light gray. So almost half the time, there was no alert. The driver would have been barreling towards off the road, and maybe they're heads down, or, like you see in some YouTube videos, maybe they're in the back seat asleep, and there would be no warning to the driver that they're headed off the road. Then for the other half of the trials, some did give an alarm, but only 21% of trials actually gave an assist. So that's pretty bad. Like, this car is supposed to detect it every time you go off the road, and really only 1 in 5 times will it ever detect and assist you. So I would call this a very unreliable system. So just to show you, there were a series of 4 tests. They were the highway lane departure construction curve. And you can go, we've got publications ad nauseum on my website that you can go read about this. This was our expectation. This was our research hypothesis for where the performance of the cars would come out in terms of complexity, you can think about this as the ice skating. How hard is a degree of difficulty here to execute, and also how well the car did execute. And so one of the things that I hope that you can see is, we had the results were all over the place. Sometimes the cars were dangerous, absolutely dangerous, and were poor in execution. Sometimes, there were a few tests where the execution was both excellent and impressive for a difficult degree, but then the alerting was really inconsistent, which raises entirely new issues. And so if you have this relationship where you hope the human is at the high end of the curve and the automation is at the low end of the curve, but these two aren't really talking to each other, then you can get a world of hurt in really easily, because what you're doing is you're breaking this, and the human doesn't know when they need to come back into the loop and pay attention because the situation deems it, or the situation needs it. And indeed, one of the things that we saw in these sets of tests were the cars were not predictable across cars, nor was one car ever predictable. The cars, you can actually see, this is why the cars have 1 and 3, 1 and 3, 2, they were very inconsistent. Even within a single car, it would not perform the same way most of the time. Again, please jump to my website if you want to read more about that. It's pretty interesting. We've also been looking at the interaction of training and autonomy. And so the military likes to, and indeed, I've spent a lot of time in Arizona, Fort Huachuca especially, because the military, depending on what branch of the service you are, has a different view. And I'm sure Hudson can add more in about this, but the Air Force insists that its UAV, unmanned aerial vehicle operators, get significantly more training. The bulk of them have to get significantly more training for the same platform that the Army will only spend a few months training people. And so in the Air Force, pilots, they get pilot training, then they move from regular aircraft to flying unmanned aircraft. And so they have a lot more training, whereas the Army enlisted people are generally just dropped right in. They go through just a few months of training to figure out how to operate a system. And so the question then became, well, who's better? Who's getting the better training? So, on that curve that you saw me show before, basically the Army operators are getting to skip the skill-based training, and they're really going to rule and knowledge-based training. Whereas Air Force operators are really kind of getting that whole curve training. And the question is, well, is one better than the other? When, why, where, and how should we think about that? So we have an indoor flight test bed, and this is a longitudinal experiment that we've been doing this now for probably 5 years. And so I'm just now wrapping up the study, thank God, because I'm so tired of running drone experiments. But we have an interface that is, we have one that's manual control that kind of looks like a virtual Xbox controller, and one that's more supervisory control, which is just click and point. So we have low autonomy and high autonomy. And then we put them through these tests, and we were really trying to dig into, how does low autonomy affect you? How does high autonomy affect you? And then one of the things that we accidentally discovered is we have this huge problem with competence. So we have a way in the lab to measure how well you think you did. So we'll run a test, and we ask you, we know how well you did, right? We know that you crashed or you didn't crash. And then we would actually ask you, well, how well did you think you did on that test? And it was amazing to me. And all the old people, Nancy will love this, and anyone over 40 is going to love this. I mean, we would ask them and they'd be like, I did great, even though they crashed. And we were like, wow, you think you did awesome, even though you crashed. Well, I mean, we would call that overconfident, certainly not self-aware, but we're calling that overconfident. And one of the things that we found from one of the studies are people who were overconfident, and these are people, and in this red circle, people who were successful were not overconfident. And again, I would point you to the papers on the website. And so we're actually digging into this more. We wanted to know, well, is there, other than we can see, if you were overconfident, you tended to crash more and not be successful. So is there a way that we can actually dig into this and figure out what exactly is going on underneath the hood, being the hood of your brains? And so I've been working on this for a long time, certainly since Hudson was a student with me at MIT. And this is a way to use hidden Markov models, which are a stochastic modeling and unsupervised. It's a machine learning modeling process. So it can get very dense. And if you want to read some super boring papers, go to my website and read all the hidden Markov models papers. So they're very dense to go through, and they're not going to be everybody's cup of tea in terms of the underlying mechanics. But what they can do, I would hope that everybody's going to appreciate, what they do for us is they help us understand people's behaviors. So we're able to actually see, we can take individual actions and cluster and see how they cluster. And these clusters of behaviors tell us a lot about how humans are aggregating their behaviors to meet some kind of goal. And so in this particular case, we know that, there's thousands of data points of when somebody's controlling a drone, they generate thousands of data points. But every series of, let's say it's a 20-minute flight, it turns out that when we look at the clusters of people who were successful and calibrated, meaning that they were self-aware, they understood that they did well and they reported that they did well. And then these are people who were successful and overconfident. We ran another experiment where we actually did have some people who were originally overconfident. Eventually they became successful, and that's people in this group. We had people who were failed and overconfident, like the picture I just showed you, and then failure calibrated. And one of the things that should jump out at you, this is a Sesame Street, which one of these is not like the other, is that indeed the people who were failures and overconfident, they just did not have the same richness of models. Indeed, you'll see that the thousands of behaviors clustered into 8 states in all the cases except for these failure overconfidence. And it tells us that they did not have their strategies, even though they went through all the same training. The people who were failed and overconfident just did not aggregate their strategies. You could actually think of it like in a structure that was repeatable to them. They were still kind of reaching and randomly executing the strategies, as opposed to getting into a much more predictable set of strategies. I don't want to spend a whole lot of time, because again, we could spend all day just on how you model people's strategies with hidden Markov models. But as a brief takeaway, I mean, clearly we can tell that there's something wrong here. And indeed, one of the things we're working on now is to see how to use these HMMs to tell, if we keep training these people over and over again, how do we know that they've gone from here to this state? To do this, we actually have to be able to figure out how to measure differences in hidden Markov models. And so if you go back to this slide, I mean, these are very serious, deep stochastic models, lots of probabilistic transitions. So how do you know, how can you do a mathematical technique to kind of roll all these in to say, okay, I had a person who was failure overconfident. I've got their hidden Markov model. How do I compare it to another hidden Markov model of the success? I mean, these are dense probabilistic mesh networks. How do we compare them to make sure that's apples to apples? And so we've been spending a lot of time looking at the underlying mathematics behind this for how to do it. Not only how to do it between these two interfaces, but you could imagine we would actually might want to say, okay, what if we modified one of the interfaces? What if we changed it and gave a person a whole new decision support tool? And indeed, that's what the cluster of these little meshes looks like up top. What if we're comparing 2 different interfaces, or maybe they're the same interface, but I modified one? Because you can imagine one of the things that these Markov models might do for you is they might be able to give you an objective way to measure people's strategies. If you add a new tool into one interface, how do you then do a comparison between the old Markov model and the new Markov model? And so, yeah, that's just what I showed you before. But to do that, this paper has just recently come out. It's on the interface. We actually then had to jump over to StarCraft. And so the StarCraft video game that many people use, it turns out that it's very similar to most of these supervisory controlled light games and interfaces that we use in the military. And so they have thousands and thousands of people playing these games, and we can get all their data. So we are able to get all their clicks and all their machinations, and the StarCraft world generates way more data than we could ever generate. I mean, a whole lifetime of my the experiments I'm running, I still cannot approximate the millions of observations that you can get in the StarCraft data. So we jumped over to the StarCraft data because it has what we would consider way, way, way more data to tell us how many, to give us all the data for each person's set of games. And the question we were asking is, how many people do you need to have? How many observations do you need to have legitimate hidden Markov models, right? So this is really important because when we run our experiments, we try to run as many as possible, but everyone on this call understands it's hard to run human in the loop experiments, way harder than people who are not in our field understand. And so what is the absolute statistical minimum that we need? And I'm not going to go through it in detail other than to show you that this is ground truth. So if we had 2,000 sets of observations for this one very narrow game, this is ground truth. We know that 2,000 observations of 30-minute games, this is what people's strategy looks like. Statistically, we don't lose that until, so 30 people is statistically the same as 2,000 people. That's actually amazing, right? That this whole part of the graph, meaning that if we have 30 people, that's enough to get you within a statistical approximation of what it is to have 2,000 people. So indeed, we've changed everything we do in my lab. We always shoot for a minimum of 30 people. I would tell you, you can potentially get away with at 20 people, you are still pretty close. Better to have 30. But for sure, if you're going to use these kinds of models or any other kind of machine learning model, you should definitely not go any lower than 20 to build an approximation. So feel free to go read more about that. All right, so this longitudinal study that I was telling you about, now we went back and ran a series of experiments because we wanted to know what's the effect of time, like, because if you are training over, and most military training happens over time, we had people have week 1, week 2, week 3, week 5, week 7. This is their completion times, and these are their crash rates. So not unexpectedly, eventually people get faster over time, and people, their crash rates get better over time. But one of the things that we saw that you can see here is the light blue is the Air Force. Hudson, you'll appreciate this. And the dark blue is the Army approach, meaning you either do all the training. So we had people do manual plus autonomy training, the Air Force way, and then we would do it the Army way, just the autonomy training, which was substantially less training. So one of the things that we found is that you get there, everyone eventually gets there, although the Air Force people do have an ability, they just tend to have a greater ability to handle problems. And oops, I don't have a picture here, but it just recently came out in a paper. In the end, our conclusions are that within a statistical approximation, you get there regardless of the way that you train. However, people who just have the autonomy training tend to be a little bit more brittle. They can handle less variability than the people who had all the manual training. And so it does, in a perfect world where we had all money and all time, it does suggest that the way that the Air Force is training people is ideal. But then understanding that you don't have all the money and all the time, our results show that the trade-offs that you make are minor enough that, you still get very good performance, although maybe not ideal. So now what we're doing is we're taking these results to see if they're going to be repeatable in a completely different interface. So we have a robot arm in the lab. That's one of the cool things that we've just done. And in case we're actually looking for subjects right now, we've actually developed an interface that allows you to remotely control a robot arm through Zoom. So this has been, it's been hard. You know, I'm a glutton for punishment, but now we have this amazing test bed, which not only can do experiments. So, you know, and if you guys are looking for other experimental platforms, we're happy to share it. But you could imagine, you could also do your own shopping through Amazon. Like if Amazon has robots picking things off shelves, why don't, instead of you know, an Amazon employee doing it, why can't you do it? Why can't you use Zoom and go into Amazon and pick your own things off your shelves, right? So we've shown that you can actually give people control, and we actually have the same thing, manual versus more automated control. And that's what we're doing right now. We're running the experiment. So let me know if you're interested in being part of that. We also have an interesting project looking at how to build simulations to optimize safety. And we're using aircraft carrier environments right now. So we're still developing the simulation, but it moves people and aircraft around on the deck, and it allows the Navy to actually start to investigate some new concepts of operation. And it actually will tell them if you start to move aircraft and people in certain ways, that these, you can see these are the hot spots where people, their risk goes way up. Okay. Yi Ren, please mute. I could see that you jumped. Thank you. And then in this top right graph, so this is the spatial risk, and this is the temporal risk. So, and this was actually brand new news for the Navy, that you could actually, we actually would see a spike about 4 to 7 minutes into an aircraft carrier launch. This is when the greatest risk would happen for them. And that's important because no one actually understood that there was a temporal component to risk. The Navy thought it was really uniform and that risk was the same from the beginning to the end. And we were able to show that it's way more weighted to the earlier minutes of the launch. And that's very practically useful, because it means that the Navy can start to move their safety monitors and start to pay more attention in those early minutes to maybe potentially mitigate some safety issues. We're also just finishing up a project where we were developing a low-cost alerting tool for drone interlopers. What this means is we've been working with prisons. So fun. You get to hang out with me and you get to go to prisons, maximum security prisons in North Carolina, but they have a huge problem where people are trying to send drones in to drop contraband, which has huge safety implications. But, you know, if you want to buy a radar from Lockheed Martin, you know, it's going to cost you millions of dollars for these small drones. It's not even clear that they work that well. So one of the things that we did was try to develop this low-cost acoustic alerting tool. We developed an app on a phone. Indeed, you could download the app right now if you really wanted it, and it will actually communicate with you when it hears a drone. And so not surprisingly, this is how it did against a DJI Phantom 4 and a DJI Mavic. You know, the further away you get from the system, the further down it goes. And this is, again, just this was round one. So we used to support vector machine to do it. Then we used a convolutional neural net in this example to do it. A convolutional neural net is really how, that's fancy AI. That's how all the computer vision is done in cars. So it's deep learning. It's a substantially more difficult algorithm to program. We did it, and you know, you could see we got better performance, although you know, still very similar performance. You know, this is the good news, is that it works-ish. Here's the bad news. I call it the old lady who swallowed a fly. For those of you who remember this, you know, there was an old lady who swallowed the fly, and then she swallowed a spider, and then eventually she swallows a cat and a dog and a horse, you know, like all these things to get to that fly. Oh my God, this is the same thing with these algorithms. First, we trained the SVM on the drone data and got okay accuracy. Then we trained the SVM on more data. But then we were having a problem with lawn equipment and helicopter false alarms. So then we ramped up our game and then tried a CNN. Okay, so the level of complexity is going up. And so, you know, then it went from a student doing it to a postdoc doing it, because we're, you know, there's a cost to that, right? So then the accuracy goes up, And it worked against some lawn equipment, but it turns out drones sound a lot like leaf blowers and weed eaters. And so then we had to add an RF detector to try to, because the false alarm problem, but the RF detector only works if people are using videos, and some drone, criminals don't use that. They don't need the video, they just eyeball it. And so it just kept getting more and more, like we just had getting more data and then more. And so the answer to all of this is, the thing that everyone on this call should remember is, machine learning, it's like you're selling your soul to the devil, because it's so brittle, it's so reliant on the data that you feed it. So the more data you feed it, the better it, you have to feed it more and more data to get it to perform at the degrees that you want. And if it doesn't, remember that stop sign picture, if you have one stop sign that it's never seen before, then it's not gonna do the right thing. And so this is really a great motivation for, you have to bring the human into the loop. And so how we changed our whole system is, now we just let the human listen to the sound via the app. So, the drone is out there, the acoustic detector gets it, we pump the sound to the human, and we let the human make the decision. And because it's just, these systems, anything with machine learning in it, it's just not reliable enough, I think, to do the signal detection in these cases where there could be potentially a lot of false alarms. Okay, what time is it? Does anybody know? I can't see my clock from here.
It is 12:36.
Oh, okay, we're doing great. Thanks, Nancy. All right, so another project that we're working on that I think it turned out to be way more relevant than I thought, and timing is everything. So a couple of years ago, Pfizer approached us and said, we are having a huge problem with our research vaccine fermentation units. So just like COVID, when they first start making a vaccine, this is one of the early units, fermentation units. What they do is they have to grow the microbial, whatever it is they're working on. They have to grow it. And so this is actually meningitis, but it's the same that they do for COVID. They grow the biological agent, then they have to make the vaccine from this biological agent, right? So these research vaccine units, fermentation units, are super important. But what happens is, there's this foam, and you need the foam because you need oxygenation inside the fermentation units. It's like beer. You've got to have some oxygen to grow the yeast for beer. Same thing inside these vaccine units. And so you need some foam, but there's no ideal foam level. At least we haven't been able to figure it out yet. So foaming to chemical engineering is the same as turbulence is to aerospace engineering. We just don't know how to solve this problem yet. So you need some foam, but the foam can grow really quickly. And if it grows too quickly, it shoots up the top and it spills out. And indeed, when we worked around these units, everybody had to be vaccinated for, you would not believe all the bad things we had to be vaccinated for. Of course, COVID wasn't around yet when we first started this program. So, but nobody in my lab is going to get meningitis. You want to stop the foam out. I mean, everybody's protected, but you would rather not expose everybody if you can avoid it, right? But to do this right now, for 16 hours, for example, a person just has to sit here and watch it. They just watch it. And you can imagine, I can't see anybody on this call wanting to spend 16 hours watching this thing. So one of the things that they've done is that they can drop in anti-foam, and the anti-foam will cut the foam down, but if you drop in too much anti-foam, it ruins the process, right? So there's a limit of how much anti-foam that you can add. But because you never know when this thing is going to spike, one of the things that we found out in the cognitive task analysis is that the operators, like, they need to go to the bathroom, for example, and it's the night shift, and they will preemptively put the anti-foam in. And then that's a problem, because they could actually ruin a batch that way, especially if they're not tracking it very closely. So they're having a hard time doing other things. So the first thing that we did is we went in and we actually designed it. It was originally designed to be on a phone, but now it's on a laptop because that's what Pfizer wanted. we call it Mind. So it's actually a system that has cameras. It actually allows people the ability to remotely monitor the system, and we actually put some alerts in there, some exception-based alerts and some time-based, and these are user-initiated notifications. I mean, they have all the alerts that would normally be available to the system, but people can add, you know, more conservative alerts, and so the system will call them. It will call their phones, or it will alert them over email that they need to be paying attention to the system because some parameter is going out of whack, and it allows them to monitor. So if they're at this critical place where they have a lot of foam, they can at least take the phone with them to the bathroom, for example, and watch what's happening and potentially signal somebody else if they start to see the foam start to rise. So that's and indeed, this was all just kind of research pie in the sky, and then COVID happened, and then Pfizer started accelerating that, because then they're like, holy crap, we've got so much more vaccine production that we need to do in this research realm, which is not now. So COVID's moved out of research. Now it's in production, except for now the COVID variants are now going through the same process, right? So you can imagine that having the ability to babysit a process remotely is important. Now, phase 2 of this is we're trying to put some machine learning, put some computer vision on it, to put the computer vision on it to predict when it's about to go out of control. So using model-based methods right now, and that would be the way that normal controls engineers would do it. It just hasn't worked, and there's a lot of, we could talk about there's a lot of detailed reasons for why it hasn't worked. So this is actually, I'm pretty hard on machine learning, particularly computer vision. This is actually one really great application because we can keep the uncertainty low. These fermentation units aren't moving, so they're still, we can watch them, we get all the contrast that we need. And so over the next year or so, the big effort that we're doing now is to see if we can actually get some predictive elements. So to give the user a warning, like, I think it's going to go out of control in the next 5 minutes, so don't go to the bathroom. Or I think you've got 10 minutes that you can go to the bathroom, but be sure to come back before 10 minutes, right? So that'd be very helpful to the user. So we'll see how well we do on this. It's hard. We're also working on developing real-time decision support for dispatchers of connected vehicles. So there's this idea that cars, whether or not they have drivers in them, are going to talk to themselves a lot in the future. So in thinking about the future of connectivity, one of the things you can imagine is if there are accidents, then you might be able to, you being a dispatcher of fleets of vehicles, for example, like fleets of Ubers or Lyfts, might be able to redirect cars early to get them away from an accident, which would both cause you not to have as much delay. And if you could reduce congestion at a certain point, it would cause us to, not be able to have so much congestion in that particular area. And there's safety implications too, access of police and ambulances. So indeed, we're going crazy. We'll have a nice demo that we'll put up in 2 weeks because we have a big deadline in 2 weeks. So we'll have a movie on my website in 2 weeks, and I'll probably tweet it out that shows what our system is capable of. So stay tuned. I just finished my sabbatical. I'm on sabbatical right now. It's a whole year. So for the first half of my sabbatical, I worked with Amazon Robotics, and super interesting. I mean, I signed lots of non-disclosures, so I can't tell you everything that I did, but one of the things that I did do that I can tell you about is really trying to help them understand the impact of these robots that deliver all these goods for people who are pickers. So these robots bring these carts and these shelves, and then the people, when you order your kombucha, it comes off one of these shelves, and then this picker puts it in these bins, and then it gets to your box and it gets shipped to you. But the question is, how have all the procedures and processes where robots are in the warehouse, how has that affected safety on the job? And so Amazon has, roughly half of their fulfillment centers are just human driven and half are have robots in them. And so this is the total injuries per 100, and these are 100 work hours, something like that. And then these are the serious injury rates. And so one of the things that you do see is that the robot injury rate is higher. So although the serious injury, this is not statistically higher, but I think this is, if I recall correctly. And why that matters is it means that there are somehow people are in some way, and these are, could be anything from like you got cut, you tripped over a robot, maybe even some repetitive stress injuries. So this suggests that we could be doing more to try to drive down the accident rates where robots are. And so, you know, we could have a long discussion about why that is and where you're seeing it. But this problem is not going to go away. And this is not just an Amazon problem. Walmart, all companies, all manufacturing that wants to put more and more robots into their warehousing environments, they need to be really sensitive to this, that when you change modes of operation, it could be because it's new, it could be because it's different, or it could be because the system wasn't designed correctly with the human in mind. So this is actually a really important result that I think is going to be more important going forward in the future. All right, so those are the projects. I just wanted to throw that out there. And then I thought we would go into questions for the last 15 minutes because, you know, I'll take questions on any of these issues.